In this video, we will solve another problem in uh, dynamics on a uniform circular motion. And this time, we will study the problems on a bank curve problem. Bank curve means it is a strategy of constructing national highway so that it prevents from danger. So therefore, the road must be inclined at an angle. So it is the usual uh, structure of the highway for every curve. Okay, so that car can move as prescribed by certain speed. So today we will study about bank curve problem. Now we have to recall our previous in our previous video in the concept of uniform circular motion that when an object moves around the curve with a constant velocity, so therefore the motion is uniform. But in a circular motion, the acceleration is not equal to zero. Why? Because we have the change in direction. So the change in direction is called as causes an acceleration which is called as centripetal acceleration. So therefore, this object, this mass, while moving around a circle, will tend to move towards the center of the circle. That's why we call this as centripetal or radial acceleration, which means that this object accelerates towards the center of the circle. Now Newton says that if we have the acceleration, then there must be an unbalanced force. And that unbalanced force is called as the centripetal force. So centripetal force is the force applied to the object so that the object can make a turn towards the curve with a maintained radius of r. Okay, so if C is centripetal force or radial force, the unit should be Newton, while AC is the centripetal acceleration or the radial acceleration, the unit should be meter per second squared. Radius r is the radius of the circle, and the mass is the mass of the moving object in kilograms, while the velocity v is the linear velocity, and the unit should be meter per seconds. So the relationship of the acceleration with velocity and mass is equivalent to acceleration. Centripetal acceleration is b squared over r. So therefore, our centripetal force must be the mass times velocity square over r. These are the relations we derived in our previous video, in video number part 1 of this topic. Then if if linear velocity is not given, instead we have the angular velocity. So therefore we will need the relations that involves linear velocity and angular velocity, and this one was also derived in our previous video. So go over our previous video. So therefore, if we substitute this linear velocity to this formula, mv squared over r, the result becomes m omega squared over r. R in the denominator was cancelled because we have r in the numerator square. So therefore, we have mass omega square or the angular velocity square times the radius. This is another way to solve for the centripetal force. Okay? So therefore, when these problems, when these formulas are applied to the problem, then you should always remember to create the free body diagram. Okay? And the unbalanced force, which is our net external force, is always directed towards the radius of the circle. So the strategy is you have to find first where's the center of the circle. And after that, create or construct all the forces acting on it. All forces that tend to move at the center will be the centripetal force. If it is towards, then that is positive. If it is outward, it is a negative force. So in this case, centripetal force is towards radius, the centrifugal is outward, which means that the opposite of the centripetal is a centrifugal force. Okay? So therefore, again, this is a dynamics of motion, so therefore we need the free body diagram. So recall our problem in the second video problem. We have this problem, a flat curved road with a radius of 230 meters. And the coefficient of friction between the two is 0.96. The car and the road, between them it has a coefficient of static friction of 0.96. The question is, what is the maximum speed that the car can travel, at which the driver can make the turn without sliding? Because too much velocity on this curve will result danger to the riders. So therefore, how much is the maximum velocity so that the car can make the turn without sliding? Okay, so we solved this in our previous video and we understand. Now take note that by constructing the free body diagram, the only force, since this is the center of the circle, because this is the object, so the center is towards right, so we constructed the Cartesian x be towards the center. So therefore, we constructed again the free body diagram. So we found out that the force towards x is the friction. Take note, friction is towards the center y, because this object will tend to move to the right, to the left. So therefore, friction is an opposing. It should be towards the right. Okay. So with that, we understand, because we know that center is to the right, the centripetal acceleration is directed towards that direction, towards the positive x. And therefore, the centripetal also force will tend or directed towards the positive x. So take note that according to Newton, whatever the direction of acceleration will be the direction of the force. Okay? So again, in this formula, the Fc from uniform circular motion, we use this one. This is Fc, or the centripetal force, is the mass times the square velocity over r. So therefore, we use this one, and take note that Fc, in this case, we have only one force, so therefore it is the friction. So substituting that where friction is mu n, so we substitute it here, and n is normal. The normal is equal to the weight, so therefore this should be mg, mu mg, and this mass was cancelled, and we have the mu sg equals b squared over r. So therefore, transforming this equation, we are able to find a relation of the velocity in terms of the coefficient of static friction and the radius. So therefore, this is the maximum. If you substitute the friction here by the gravity and r, taking square root of that, the result is the maximum velocity that the car can provide in order to make a turn without sliding around the curve. So we calculated this in our previous video, and we found out, substituting the values, we found out that the maximum velocity can the driver have, its velocity magnitude is only 46.54 meters per second, which means that if you travel above this value, then you cannot make the turn. Okay? If you travel at this value exactly, then you are traveling at the maximum required speed. Below is a safe velocity. Okay? So, the question now is, if this is the maximum velocity required for a car to travel without okay, without, okay, can make the turn without sliding. So what will happen if you want to move this curve with this velocity? The question is, can we do it? Okay. Now, if you stay on this road, which is a flat road, then therefore you cannot travel at the speed of 50 because 50 is more than 46. So what is now the strategy? The strategy is to use a bank angle. This is the bank angle, meaning you have to incline the surface of the road. Okay? So therefore, if you want to have this velocity, the strategy is to bank the road at an angle theta. The question is how much theta do we need in order to travel? Okay? That will be our task for today. We will derive a relation in such that we can provide how much is angle for a given speed. Take note, why is it that this is the solution to have more velocity requirement? The reason is look at the normal force. in the previous figure, this normal is lying along the y. So therefore, y normal force don't have the contribution towards the center of the circle. Now in this case, the normal have its component along x and along y, wherein the along x will be a contributor towards the centripetal force, which means that the normal force component along x help the friction to produce the centripetal force. It is not only, if you remember previously, this one, in this problem, we have only the centripetal force friction. So in this case, in this configuration, we are now adding the value of the normal force component along x. So it should be the normal force along x added by the friction. Okay? So, and we can ignore this one. We can ignore the friction if you want to. If you want to ignore this one and let the normal force carry on that force, then you can do it. Okay? You just increase the angle. So take note that n now has a component along y and component along x. This in x contributes towards the centripetal force because this force tend to move towards the center of the circle. Okay? While in y doesn't contribute. But this one, the task of ny is to let the object stay on that surface. So therefore, in order to stay the object in contact with the surface, the normal should be equal to the weight. Normal along y should be equal to the weight, not the normal value. It is the component of normal along y should be equated to the weight to make it balance. And nx will be our centripetal force. So therefore, if we ignore the effect of the friction, let's say the surface is very smooth, we ignore because the friction is negligible. So therefore, you can ignore it. Then let nx carry the centripetal force. Okay. So the question now is, how will you tilt your surface or bank your surface? Is it in both ways, meaning we can tilt it right side or left side? The answer is depending on the curve. If the curve is just like this, this is curve towards right, so therefore your bank angle should be tilt towards the right also, which means that this is the correct bank curve. Whereas if you reverse it, this is a wrong process for a curve directed towards the right. So therefore, we have to use this one. So the question now is, how much angle do we need for a certain velocity and a certain radius? Take note that this angle depends on velocity and depends also the radius of the circle. So let's derive the formula. So all you need to do now is to construct again the free body diagram. But before that, you have to overlay the Cartesian. Then take note that the center is towards right. So we assign this x as is. because x is directed towards the right, which means that our acceleration is towards right also with our centripetal force. Okay? Then, identify all the forces on the car. We have the weight and we have the normal force. Okay? Now, take note that we ignore the friction. So, forget the friction. Now, then all you need to do is to resolve into its component. Now, take note, if this is the bank angle is theta, this is also theta. Why? Because if this is 0, this is 0. This is by geometry principle. So, we are now ready to resolve the normal force into its component along y and along x. Okay? So, we notice that nx again is directed towards the radius of the circle, which means that this is our centripetal force. Now, we need to resolve the into its components, so we have to solve for ny, and we have to solve for nx. So ny in this case, since ny is adjacent to this angle, so we have this as cosine. Now take note that these three vectors, the nx, ny, and n, forming a right triangle because this n can be constructed here. So it will coincide exactly at that point. So we have this as a right triangle. Okay? So if this is theta, this is also theta. Okay? Or this x can be constructed here. So this is adjacent over hypotenuse. That's why cosine. So nx is the sine. So we have now this value. Okay? Now, if you sum up all forces along y, the force along y are the weight and the normal along y, in y. So therefore, in y, which is positive, the weight is negative equal to 0. So we can say that the normal force along y is equal to the weight again. So therefore, this is to ensure that there was a contact between the car and the surface. So therefore, this must be set to 0 for equilibrium purposes. So therefore, in y again is equal to mg. But what is in y? In y is in cosine theta. So therefore, replace this with in sine cosine theta. So therefore, this is the result. Okay? So in this case, we can now solve for n. And this is in terms of the mass and the angle. So therefore, transform it or divide both sides by cosine. Our n is mg cosine theta. Okay, we are done in the process of solving our normal force. Normal force is important not for friction, but this is for the component of the normal along x. Okay, so next is to sum up all forces along x. We understand that if we sum up all forces along x, the answer should be not equal to 0. Okay, because the object requires to make a turn in the curve. So therefore, summing up all forces along x, we have only in x. Take note, we ignore the effect of friction. So if we ignore the effect of friction, it is more safe if we do it in the actual situations. We ignore the friction. We consider only the normal force. So what is the angle? That is our task for today. So take note that in x is in sine theta. Okay, in x is in sine theta. So therefore, take note, this is the net external force. This is the net external force. So therefore, in that case, we will use the formula. We will not use the second law. We will use the uniform circular formula. And this is if C is equal to mv squared over r. Okay. Then take note that if C is the centripetal and this one is the net external force. This is a centripetal force. So this must be substituted here. So therefore, this must be if C becomes n sine theta is equal to mv squared over r. Now, what is n? N is this one, mg over cosine. So we will replace this with mg over cosine theta. Okay, that's it. Now, take note that the mass here can be cancelled in the mass in the opposite side. So, mass will be eliminated. Then, what is sine over cosine? In the fundamental identity, Sine over sine is tangent. Okay, in trigonometry, this is tangent of theta. So therefore, since mass already cancelled, so what we have now is we have g tangent is equal to b squared over r. Okay, actually, this is now the relation that we are looking for. So, if I divide both sides by g, so therefore, we can say that the tangent of theta is equal to b squared over gr, where g is the Earth's gravitational acceleration, r is the radius of the circle. Which means that our bank angle, take note, this is the bank angle, in relation with the velocity and r, it is directly proportional to the square. Meaning, the greater the velocity, the greater the angle requirement. And the greater the radius, the smaller the angle. So therefore, this is the relation of the bank curve problem, bank curve road problem. The highway engineers in designing road, they use this relation in order to decide how much angle should be banked to the road in order to produce the that velocity required in order to prevent from traffic. Okay, so for example, we want to solve for the velocity. How much velocity if we have already the constructed bank road, bank curve? Suppose the curve has already constructed and we found out that we have that angle. So the question is, what will be the maximum velocity in that curve? So all you need to do is to transform this one, solve for the velocity, take square root, okay, and this is the formula. So in order to know how much velocity requirement for that angle, because r is already constant, and we have this as our variable, so therefore substitute it here, okay, that angle, then the result will be our maximum velocity for that angle. Okay, so therefore it is directly proportional. The greater the angle is, the greater the velocity requirement. Okay, suppose we will reverse the process. We want to know how much is the angle if you want to have that velocity. For example, in our previous problem, the velocity requirement is, the maximum is 46 point something, and you want to have it 50 degrees. So you have to substitute it here. Okay, then solve for the angle. Take note that we can solve this angle, no? Take the inverse tan of the b square over gr. This is gr. So therefore, substitute the velocity here, substitute the radius, then take the inverse tan, and you will be calculating the bank angle. Okay? So, this is it. These are the formula. The important formula in the bank curve road problem. Now, let's have the actual problem or situational problem. Suppose we have the radius to design by a 230 meters radius road, and this is bank road. Okay. And the velocity is 25 meter per second. Question: what should be the bank angle of that pavement? So, if you are answering this one without knowledge about the bank curve, you cannot solve this one. Okay? So, since we know already what, there is no specified here about the friction, so ignore the friction. Do not mind for the friction because the question is how much the angle. Now, if you answer that angle, it is more safe in the actual, because in the actual there is always friction between the tire. So therefore, more safe. Okay. So how much is the angle without the friction? So then, all you need to do is to use this formula. Substitute the angle. This is 25. Square it. Divide by z. Divide by 230. Then take the inverse tan. And the answer is 15.48 degrees. Okay. So, okay. Then, if you want this to be 50 degrees, then square it. Or 50 meters per second. Then, square it. Divide it by these two. The same. Reduce. inverse tan, then you have more angle. Okay, because more directly proportional. Your angle, bank angle is directly proportional to the square of your velocity. Okay, so this is a challenging problem. This is good for the highway engineers for designing the road for the bank road curve. Okay, so in order to exercise again the concept discussed in this video, you are encouraged to solve this problem. We have the 1,200 kilogram car rounds a curve at a radius 65 meters and the bank angle of 14 degrees. If the car traveled 80 kilometers per hour, will a friction force be required? Okay. If so, how much and what direction? Okay, this is a very nice problem. Okay. So, good luck. Good luck. Solve this. Thank you.